So today I'm going to talk about how you can grow oxide thin film for magnetic application. I mean, I'm not sure I will have time for health applications. And this work was done. Let me see if I can start a pointer. This work was done in collaboration with my group in University of Caen, which is located in Normandy, and it's a collaboration with University of Liège in Belgium, and some people in IIT Madras, Chennai in India, and also from Hankook University in Korea. So this will be quickly the outline of my talk. I mean, after a small introduction, I will show you how we can prepare some oxide thin film for magnetism, and I will show you the growth of praseodymium vanadate and thin film, the structure, some DFT calculation, and then I'll finalize with the magnetic properties of PrVO3 thin film, and I will show you how we can work on and play with the strain and the thickness before I can conclude. So you probably all have known that in transitional metal oxides, I mean, there is a wide range of functional properties which include insulator, metal, superconductivity, and also ferroelectricity. And basically, when you look at the Mendeleev, the table, I mean, you can see that some of them will be more dedicated to metal, like chromium oxides, or titanium will be mostly ferroelectric. If you want to learn about superconductivity, you will be using mostly copper oxide. And another way of looking at them is to look some, I mean, that's what we decide, is to grow some lanthanum vanadate thin film. And why we are looking at the vanadate, it's basically because if you look at this diagram, you can see as a function of the size of the rare earth, so going from lutetium to praseodymium, you can change the size. This will change the size of the ionic radius. And with this, you can also change the properties. And you can go from something with a G-type orbital ordering, a C-type orbital ordering, and so on. And basically, what it means is that you have a strong interplay between orbital order, spin order, and lattice distortion. And in fact, what is also in particular interesting is that taking this phase diagram, you can see where you plot both different composition. And in fact, you can also see that all of these properties can be tuned as a function of the magnetic field. This is sort of external pressure. Sorry, not magnetic field, pressure, hydrostatic pressure. And in fact, the idea of this work is to try to correlate what you will do with the pressure. And you can consider that by growing a thin film, which is strained within a substrate, you do this. It's because we believe that you can find some similar properties as you will find with pressure when you grow a thin film. From Switzerland, where they show that if you grow, you see, in that case, okay, angles and so on will be different. In other case, the tilting of the octaedra will be different. That's the way the film will accommodate to the strain. And another way of accommodate the strain will be by having some defect. Two types of defect, basically, either a cationic defect or anionic defect. Basically, you have some oxygen vacancy. And the idea of this work is specifically to understand and to see if we can control the oxygen vacancies in praseodymium vanadate thin film and see how you can modify the properties. And also, how does it affect strain and thickness effect? So what we did is, we grow some praseodymium thin film using shining on the substrate, on the ceramic, and under the impact of the laser. I mean, you will have a formation of a plum, and within this plasma will be condensate directly on the substrate, which is heated at typically 700, 800 degrees Celsius, and that's a way to Hertz, and the film is grown between 500 and 800 C under vacuum. And here is a typical X-ray diffraction that we have been obtaining. So theta to theta scan, where you see here the main peak of the substrate, the 001, and you also see here, very close, a beautiful peak which corresponds to the 110 direction of the praseodymium vanadate, and with some oscillation which indicate that the film is of a very high quality. We also look at the X-ray diffraction, and you can see from this picture that we have phi scan, so it means that the film is grown cube over cube, We also see from the reciprocal space map that along the out of plane direction, the film along the in plane, because in that direction it's aligned. So along the in plane direction, the film is aligned with the lattice parameter of the substrate, whereas there is a small change in the out of plane direction. And so that's the reason why there is a difference between here and here, between the peak of the substrate and the thin film. And you can see also this in this graph where you have the lattice parameters also as a function of pressure. You can see that as a function of, let's say, depending on the condition, the C-axis can be changing, but the A-axis is always kept at the same value, which is very close to the bulk, and also very close to the lattice parameter of the substrate. Strontium titanate, just to remind you, it's about 3.9 angstrom. So what you see from this graph, depending on your growth condition, you can modify the